The aircraft is a world unto itself. It glides through the thin, cold air at 30,000 feet. Inside, passengers are calm. They read. They watch movies. The steady hum of the engines is a constant, reassuring sound. Then, that sound disappears. A sudden deep silence fills the cabin. The lights flicker once, then die. Emergency lights cast a dim, strange glow. In the cockpit, a symphony of alarms begins to chime. Red lights flash across the instrument panel. Amber lights flash across the instrument panel. The pilots are no longer just flying. They are now in a fight to save the aircraft. Their training takes over. Every action is precise. Every decision is critical. They must restore power to the systems that keep this metal bird in the sky. The loss of all engine power is one of the most serious emergencies a flight crew can face. The aircraft becomes a glider. But it is a very heavy, very complex glider. Without power, the advanced flight controls and digital displays go dark. The pilots lose the tools they rely on to navigate and control the plane. The stakes are incredibly high. The pilots must act quickly. With the engines out, the plane is now a glider. Its forward motion is its most valuable asset. But to control the aircraft and land safely, they need power. This is a scenario engineers have planned for, with systems designed to work when all others fail. In a total power failure, pilots lose their most important instruments. Without the engines, the main source of that power is gone. Hidden in the aircraft is a final, mechanical hope. A small door opens, and a device deploys into the rushing wind. This is the Ram Air Turbine, the RAT, a silent guardian, designed to work when everything else has stopped. Few moving parts, purely mechanical function. Once deployed, the RAT immediately begins to spin. The wind over its blades forces rotation, like a pinwheel in a strong breeze. A small wind turbine, purpose-built for aerospace. Size varies by aircraft. Wide body, a few feet in diameter. Business jet, much more compact. Same principle across designs. It harnesses kinetic energy from the air and converts it into usable power for the aircraft's most vital systems. This spinning propeller is the first step in restoring control. A lifeline for pilots in their moment of need. Passengers rarely see it or know it exists. Its presence shows aviation's layered safety. Engineers planned for the what-if scenarios. The RAT answers. What if the engines go quiet at 30,000 feet? It gives pilots fundamental tools to fly. A bridge between total failure and a chance at a safe landing. The science behind the Ram Air Turbine is a direct application of aerodynamics. As the aircraft glides through the air, that air has energy. The RAT's blades are shaped like small airfoils designed to capture this energy efficiently. Marketing. Detailed shot from a maintenance hangar showing technicians inspecting the blades and housing of a RAT. The airflow pushes against the blades. The faster the aircraft is moving, the faster the RAT will spin and the more power it can generate. This is why airspeed is so critical during a dual-engine failure event. Pilots must maintain enough speed to keep the aircraft flying and to ensure the RAT can do its job. It is a beautiful, direct conversion of motion into power. The spinning of the RAT's blades drives a shaft. That shaft connects to critical components, a hydraulic pump, and electrical generator. In most designs, the RAT powers the hydraulic pump first. Hydraulic pressure is the lifeblood of an aircraft's flight controls. It moves the massive control surfaces, ailerons, elevators, rudder. Without hydraulic pressure, moving them would be like steering a bus with no power steering. The RAT provides enough emergency pressure for pilots to maintain control. It is one of the most important emergency backup systems. The RAT can also power a small electrical generator. It won't run cabin lights or entertainment. Its purpose is far more critical. It powers the essential cockpit instruments, airspeed, altitude, heading. It can also power navigation systems. A famous example of the RAT in action is U.S. Airways Flight 1549. Shortly after takeoff, a bird strike caused catastrophic failure of both engines. The aircraft's systems automatically deployed the Ram Air Turbine, supplying vital power to the flight controls and primary displays. This enabled the pilots to ditch the aircraft in the Hudson River, saving all 155 people on board in the Miracle on the Hudson. A dual-engine failure is exceedingly rare, but aviation safety is built on preparing for such rarities. This is where backup systems like the Ram Air Turbine come in. The story of U.S. Airways Flight 1549 is a powerful reminder of the synergy between human skill and engineering foresight. The pilots are the heroes, but the rat is their silent partner. If the Ram Air Turbine is so useful, why not use it all the time? The answer is a series of trade-offs. When deployed, the rat creates significant drag, increasing fuel burn. It also adds weight and cost for purchase and maintenance. For emergency use, the trade-off is clearly worth it. For everyday flight, it is not. The Ram Air Turbine is a study in contrasts, a simple mechanical device hidden inside a much more complex airplane. It remains dormant for thousands of flights, yet must work perfectly on the one flight it's needed. It generates power not from fuel, but from the aircraft's motion as it falls. The rat is not the hero. The pilots are. The rat is the tool that enables their heroism, giving them the means to fight back. Hidden systems run our modern world. Good engineering is often invisible. The Ram Air Turbine is a small hero for the sky, a quiet guardian for when things go wrong. Understanding these systems replaces fear with fascination. If you value the hidden genius that keeps us safe, subscribe to Hidden Engineering. Stay curious.